I thank the organizers for this opportunity. I'm Young-Ok Lee from Yonsei University in Seoul, South Korea. My team at Yonsei is getting very interesting and perhaps very challenging result in our long-term investigations in supernova cosmology. So today I'd like to share some of them with you. As you know, the supernova cosmology is still providing the most direct and the most strongest evidence for an accelerating universe. It is a very simple method based only on the Hubble diagram, basically luminosity distance and the redshift. And as we know, everything started from supernova cosmology 24 years ago. I would like to remind you that what they found is that the supernovae at high redshift are fainter by only 0.25 Mach. That is only 20% in terms of the brightness compared to the model without dark energy. And this was interpreted as evidence for an accelerating universe with dark energy. But an alternative interpretation is also possible because as Beatrice Tinsley pointed out very convincingly a long time ago, the stellar populations in host galaxies are getting younger with redshift. Therefore, it is equally possible that the high redshift supernovae are fainter, not because of the dark energy, but because their progenitors are simply younger compared to their counterpart at the local universe. And history tells us that we should be concerned on this possibility. There are many examples, but for example, in 1944 and later, Bade discovered that the young population one Cepheid that Hubble discovered in M31, the Andromeda galaxy, are in fact brighter than old population 2 Cepheid, based on which Hubble mistakenly calibrated his observations. So because of this well-known history, the distance to M31 and all other galaxies has been doubled, and the value of H0 has been decreased by a factor of 2. So this illustrates that the luminosity of a standard candle can actually depend on stellar population age, most likely because of the difference in mass. And indeed, during the last decade, supernova host galaxy studies found correlations with host mass and the local star formation rate. And as these authors suggest, these correlations, the root cause of these correlations are most likely due to population age. However, reliable population age dating for host galaxies was lacking in the literature. Here, the key parameter is the population age, but the data was simply lacking in the literature. So some 13 years ago, we have decided to measure very reliable population ages for the host galaxies by obtaining very high quality spectra for some 60 nearby early type host galaxies. We call this project Yonsei after our institution, Yonsei Nearby Supernovae Evolution Investigation. We spent a lot of time for this project. After some 9 years of hard work, we found an important 3 sigma correlation between the population age of host galaxies and the Hubble residual, which is a measure of relative luminosity. And this result is not sensitive to the choice of the population census models. And the sense is that the supernovae in younger host galaxies are in fact fainter than those in the old host galaxies. And high redshift supernovae should be similarly fainter because they should be also from the younger progenitors. We also found that our result from directly measured ages is fully consistent with previous investigations based on age proxies, such as host morphology, host mass, and local star formation rate, and when they are converted to age difference. So they are all pointing to the same direction. Supernovae 1A in younger galaxies are fainter. Soon after our paper, Adam Liss and Ben Rose and their collaborators claimed that our result from early type galaxies, elliptical galaxies, are not confirmed from a larger sample of host galaxies comprising all morphological types. And their claim was based on the 2 age data sets, all measured from multiband photometry. It turned out, however, their first plot in the right panel is a seriously flawed result based on unqualified, unpublished age data without error bar for the ages. And we found that their error bar could reach up to 10 gigayear. So basically, this is a meaningless data set. In any case, in science, I would say that the data without error bar is not even the data. So we can completely ignore this. The other plot in the right-hand side is quite reliable mass-weighted ages for host galaxies. But this time, we found a serious problem in their statistical analysis because of the regression dilution bias. To make a long story short, for the same data set, we performed a standard MCMC method for the regression analysis. And in a surprising reversal, we found a strong 4.3 sigma correlation between population age and Hubble residual, both for the global ages for host galaxies and local ages near the supernova site in a host galaxy, in excellent agreement with our previous spectroscopy result from early type galaxies. So this is our rebuttal paper. And so even the data set originally used by Rose and Liss et al. To oppose our claim is instead strongly supporting our result. And we have a third-party confirmation for this 5 sigma correlation from the UC Berkeley team, and now also from a Chinese team, Wang et al. Paper. So I was wondering, why are you getting this correlation between population age and supernova luminosity after luminosity standardization? So in order to understand that, we need to understand the supernova 1A luminosity standardization process, which is based on the light curve width or stretch parameter x1 together with the color parameter c. Like the Cepheid period luminosity relation, type 1A supernova luminosity standardization is based on the width luminosity relation, WLR, and the color luminosity relation, CLR, where the slopes for these relations are alpha and beta in this luminosity standardization equation. And as these reading also emphasized, the key assumption in supernova cosmology is that these relations should not depend on progenitor age, because high redshift supernovae should be from younger progenitors compared to their counterpart at local universe. So in order to check that, we plotted WLR and CLR for the same Rose et al. Data set. You can see the log correlation with luminosity relation and color luminosity relation, but you can recognize a huge scatter at given x1 and given c. So now we will subdivide this sample into 2 according to the population ages, young and old subgroups with some gradient between. And this is the result. Supernovae from younger progenitors in blue, and those from older progenitors in red. And surprisingly, there is a strong progenitor age dependence in the sense that the younger progenitors, supernovae from younger progenitors are fainter, each had given light curve parameter x1 and the color parameter c. And this is a 4.6 sigma result. And we also tested other host properties, and they show substantially smaller and insignificant offsets, indicating that progenitor age is the root cause of the reported correlations between host properties and Hubble residual. And this luminosity offset at given x1 and given c is reminiscent of Badel's discovery of separated period luminosity relations varying with population age, as we have already seen here. And as such, this must cause a serious systematic bias in supernova cosmology. This is before the luminosity standardization, and after the luminosity standardization, which is nothing but the rotation of these diagrams following the slope alpha and beta. So this is before, and this is after. Before and after. So after the luminosity standardization, the young supernovae in blue are overcorrected and become fainter. So high redshift supernovae are also from younger progenitors, and therefore should be equally overcorrected and become similarly fainter. So this suggests that the observed extra dimming of high redshift supernovae is most likely due to a stellar astrophysics effect rather than cosmological effect. We can actually calculate how the stellar populations in host galaxies and how the supernova progenitors are getting younger with redshift, which is well supported by observational data. And within the redshift range, most relevant to supernova cosmology between redshift 0 and 1, and we have roughly 6 gigayears of variation in population age. So we can make a correction. We can make a correction with the progenitor age bias to the observational data as a function of redshift. So this is before the age bias correction. We can see that the supporting all the data points from JLA, the bin data, is supporting the LCDM model. And this is after the age bias correction. And we can see after the age bias correction, only there is little evidence left for an accelerating universe. And in the flat WCDM model, roughly 10 years ago, when the measurement errors were larger, there was apparently a good concordance in cosmology. Supernovae, CMB, and BAO, when they are combined together, they support a W value of -1, the equation of state of dark energy. However, in 2023, even before our age bias correction, note that BAO and CMB, they barely overlap. However, the supernova result is right in the middle. Therefore, when 3 of them are combined, they still apparently suggest W value of -1. So in this sense, supernova data is playing a very important role in getting the W value of -1, the cosmological constant. Now, after our age bias correction, supernova data is moving up And very interestingly, they agree with the BAO. However, they are in discordance with the CMB. So after the age bias correction, we have a strong tension, strong W tension, 6 sigma tension between the Roche probes, supernovae, and BAO, and CMB in the flat WCDM model. And this is probably not very surprising because we already have the Hubble tension between supernovae and CMB. So just like the Hubble tension, now we also have the W tension between the Roche probes and CMB after our age bias correction to the supernova data. And it is interesting to note that another team in Korea, led by Chang-Bon Bak, found that the Alcock-Pazinski test, another Roche probe, also prefers W value larger than -1. So the Alcock-Pazinski test is also somewhere here. So now the situation is very different from that of 10 years ago. We have no concordance, but strong discordance in cosmology. And especially after our age bias correction in supernova cosmology. So let me summarize. The supernova cosmology is based on such a fragile assumption, which is no longer supported by our discovery of strong progenitor age bias in supernova luminosity standardization process. And when this systematic bias is fully taken into account, we have a strong W tension between the Roche probes and CMB in the flat WCDM model. And I think this is quite a very robust result because we went through all the debates during the last 3 years or so. But because of its important implications on cosmology, of course, we are performing follow-up investigations for a larger sample of host galaxies at different redshift fields. So we welcome your collaborations. Thank you.